Hello class, this is CSE-4600, section 62, week 14, fall 2024. We are nearing the end. So we're going to continue our discussion on memory. Specifically, we're going to look at the page table and a few page replacement algorithms, because there are 2 points to consider with a paging system. 1, we need a data structure to contain information about what pages are and are not loaded into memory. This is called a page table, and there are different ways of organizing the page table. Also, when a page was not loaded into memory, we need to make room for that missing page. We need some means of selecting a page frame in which to load our missing page. Ideally, we should select a frame that has a page that hasn't been used in a while, or better yet, we select a frame with a page that we know will never be used again. I'll get to that in a little bit. So as a recap, early computer systems can only load one process at a time. For systems that could have multiple processes loaded, it could be such that you can only swap out one process to make room for another process. So you can have multiple programs, but not at the same time, not running at the same time. Systems that could allow for multiple processes to run at the same time needed special hardware to make sure that a process didn't accidentally jump into another process's memory. When we get to paging, basically the idea is this. We cut up a process's address space into pieces and we load those pieces as needed. This was in the early days, this was done manually, but why do something manually when you can just have a system that does it automatically? It's through these mechanisms that we get modern day paging. A process, as far as I can tell, has access to a large virtual address space. That address space is cut up into pages, and they are loaded into page frames. Physical memory is cut up into page frames. The virtual address space is cut up into pages. 1 page per frame. We load pages as they're needed. If a page being accessed was not in memory, then that results in what is called a page fault. The OS then must send an I/O request to the disk to load the missing page. Then it must select a page frame in which to load the missing page. There are algorithms for this as well. So it's one thing to request an I/O operation to load the missing page from the disk. It is another thing entirely that we will get into as a topic of this discussion of selecting a page frame in which to load our missing page. Information regarding each page is stored in a data structure called a page table. This includes what physical frame each page is loaded in. This also includes information on whether that page was loaded into memory to begin with. We use this information to convert virtual addresses into physical addresses. So we can see this in the 16-bit example here. So this virtual address simply means page 2 offset 4. The high order bits form the page number, the low order bits form the offset. So this is basically 2 binary numbers that we can interpret into base 10. And when we do that, it simply means page 2 offset 4. Which is something that the program can understand. The hardware does not understand that. It needs to convert that into something it can understand, and that is a physical address. So let's take this address and feed it to the memory management unit. That is where the page table lives. Or rather, this is what the... Well, actually, this isn't where the page table actually lives. We'll talk about more we'll talk more about that later. But when we present this address to the MMU, it looks up page 2 in the page table. And here it is. This means we have the page loaded into memory, and it is in frame 6. We use that information to turn page 2 offset 4 into frame 6 offset 4. That is something that the hardware can understand. So, interesting thing to note here, the virtual addresses are 16 bits, but the physical addresses are 15 bits. And that is because we only have room for 8 pages. There are only 8 page frames, therefore there's only room for up to 8 pages to be loaded. So, what's going on is this. The virtual address space, through paging, the virtual address space can be larger than the amount of physical memory on the system. The term here is oversubscribed. So oversubscribing is where a resource is allocated to more than one process. This isn't really happening here. For this one example of a single process, it's one page frame being used for different pages. But this doesn't really hurt the program. Well, it can hurt the program in ways that we'll see later on, but basically the idea is this. When a process runs, it only accesses a handful of pages the most frequently. Less frequently used pages, we can just load them in and out as needed. For the most frequently used pages, they can just stay constantly loaded into memory. This reduces the amount of memory that we need for each process. This frees up more memory that we can use for other processes. This increases the degree of multi-programming. This means a system can run multiple processes at once. So all of this is interconnected. So the degree of multi-programming is the number of processes a computer system can run at once. If we free up memory by doing paging, then that's more memory that we can use for more processes. Okay, let's check out the page table. So the layout of the page table depends on the machine, but it's going to convey the same information. You can think of the page table as a table of contents, except some of the entries don't lead anywhere, and this is a table of contents that changes over time based on pages being added and taken out. Each entry in the page table has a valid invalid bit, or at least that's what other textbooks call it. This textbook calls it a present absent bit. So if that bit is 1, that means the page is loaded into memory. So associated with each page, not just the present absent bit, but also the page frame as well. So each page has a entry associated with it for the page frame, but also a valid invalid bit. If that valid invalid bit is 1, that means the page is loaded into memory, and the field for the page frame is also valid. That means we can find the page at that frame. If that bit was 0, then the field for the page frame is invalid. That means that page is not loaded into memory, and if you try to access it at that page frame, it's an invalid memory access. Really what happens is we just get a page fault. There's more information that is also stored for each entry in a page table. That information includes a reference bit. If that bit is 1, that means sometime after the page was first loaded, it was accessed. And another one is called a modified bit. That means sometime after the page was loaded, the contents of the page were changed. This could be a field that changes over time, so at one step it was 29, and another step it was 31. It's also called a dirty bit. We won't discuss the following fields in depth, but there are other fields. That is the protection bits and the caching disable bits. Really, we're not going to talk about it in depth here, but the protection bits define what kind of access modes are allowed on a page. So, to reiterate, virtual memory creates an abstraction of a memory space that may be larger than the amount of physical memory on the system. The term here is oversubscribing. Virtual memory can be broken up into pages, and we map each page onto its own page frame. Not all pages need to be loaded. There's not enough room to load every page, but that is okay. A process simply accesses a small handful of frequently accessed pages, so we can get away with not having to load the whole process at once. And it is the responsibility of the operating system to create and manage this abstraction here. So let's talk about speeding up paging. So in a paging system, we need to address 2 issues. First, the mapping from virtual address to physical address must be fast. So this the sequence of steps needed to convert a virtual address to a physical address, that must be fast. Also, if we have a large virtual address space, then that means we have more pages we need to have. Now, if the virtual address space is large, so will the page table. That means we need more entries, making our page table larger. What can also affect the size of a page table is how small the pages are. If we have lots of small pages, that means we need more entries in our page table. We can mitigate this by, well, having larger pages. Although this isn't really discussed in the textbook, having larger pages does have a downside. Imagine you have a process that takes up 4097 bytes. 4097 is 1 more than 4096, which is a power of 2. Our page sizes are powers of 2, by the way. If we have this 4097 byte process loaded into memory, that means it takes up 2 pages. The first one is filled to the brim, and the second one only has 1 byte loaded into it. The other 4095 bytes in that second page is wasted space. We can mitigate the effects of that wasted space, called internal fragmentation, by instead using smaller pages. So if we have instead 1024 byte pages, then we would need 5 pages, and the first 4 will be filled to the brim. The 5th page is going to have 1 byte loaded, and the other 1023 bytes of space are wasted space, which is better than the 4095 bytes of wasted space that we had if we were using 4096 byte pages. So yeah, that is one consideration that isn't well discussed in this book. That is, the larger the pages are, the fewer pages we need to keep track of. But the larger the pages are, the more wasted space we have for that last page used for each process. Okay, so let's get back to the issues with speeding up paging. The first one is the mapping from virtual addresses to physical addresses must be fast. Remember, the process only works with virtual addresses, but the hardware expects to see physical addresses. The sequence of steps needed to convert a virtual address into a physical address, this takes time, and we want to reduce that time to be as little as possible. For point 2, most machines are either 32-bit or 64-bit. If the machine you're viewing this on was made within the last decade or decade and a half, then there is a good chance that it's going to be 64-bit. There are some 32-bit systems still on the market today, but most systems are probably going to be 64-bit. A 32-bit machine simply means it can access 2 to the 32nd power unique memory addresses. This equates to 4 gigabytes of memory. 64-bit systems means they can access up to 2 to the 64th power memory addresses. So this is not 32 times more than 32-bit. It is 32 more doublings after that. If we have a 4 gigabyte memory space cut up into 4 kilobyte pages, that 4 kilobytes, really that means 4,096 bytes. That is 2 to the 12th power. If we divide 2 to the 32nd power, which is 4 gigabytes, which is 3. Okay, so 4 gigabytes, we really mean 2 to the 32nd power. If we divide that by 4 kilobytes, which really means 2 to the 12, that is 2 to the power of 32 minus 12, which is 2 to the 20th power. 2 to the 20th power is about 1 million, which means 4 kilobytes times 1 million is 4 gigabytes. This also means we need 1 million pages. If we wanted to page the entirety of a 64-bit address space using 4 kilobyte pages, we need something on the order of 10 to the 15th power pages per process! It means our page tables are going to become huge on a 64-bit system. So yeah. Okay, so we need fast page mapping. The need for large fast page mapping is a significant constraint on the way we build our computers. We could have the page table loaded into special hardware that makes accessing these entries as fast as possible. This of course speeds up accessing the page table, but it makes the system more expensive because the hardware needed is itself expensive. Plus, we gotta context switch this information every time we context switch processes. So, we could have the page table loaded into special hardware, but that is expensive. But what if we didn't need to load the whole thing at once? Can we do that? And the answer is yes, and I'll get to that in a little bit. If we don't have special hardware, then at worst, we need to have the page table loaded into memory. Which means if we need to access something in memory, we need to access the page table in memory so we can figure out where in memory to access our address. Basically, we need to do a memory access every time we need to do a memory access. So that is 2 memory accesses. That slows down the program. And we don't want that. If the program slows down, it's going to make the program look unresponsive to the end user, which is undesirable. So let's look at using special hardware. Can we use special hardware, but only for the pages that a process is accessing the most frequently? The answer is yes. It's been observed that when a program accesses memory, it does most of its accesses on a handful of pages. So, all you gotta do is keep track of the most frequently accessed pages and only use the special hardware on those entries. If we want to speed up paging, all you gotta do is use it only on the most frequently used pages. This saves on hardware cost. This hardware is called a translation look-aside buffer. It's basically a cache for the most frequently accessed page table entries. There's only room for about a few hundred page table entries in here. Rarely does it ever exceed 256 entries, but that's okay. When we present a virtual address to the MMU, we first check whether that entry, we first check whether there's a corresponding entry in the TLB. When we look for a virtual page in the TLB, say we're looking for page 129, basically we check the page against every entry in the TLB all at once, in parallel. This speeds up checking the TLB, so not one entry at a time. We check all of them at once. If we find a matching page that doesn't violate the protection bits, then we have what is called a TLB hit. That is good. If no match was found, then we have a TLB miss, which is bad, because the MMU must then look up. I have another typo in the slides and it's messing me up. Basically, if the page we're looking for was already in the TLB, that is a TLB hit, that is good. We don't have to look into memory to look for the page information, because accessing memory is slower than accessing a cache. If we have a TLB miss, that means we have to look into memory for that information. Well, here's the thing. If we need to access that same page again that wasn't already in the TLB, then we're simply gonna put that page information as a new entry in the TLB. An entry in the TLB is copied back to the page table to make room for this new entry, however. So, the content here assumes that the handling of TLB misses is done by the hardware. In many cases, this is done by the software. This has a few considerations though. If a TLB miss occurs, and TLB misses occur often, it is thrown to the OS, which is responsible for loading TLB entries and removing TLB entries to make way for new TLB entries. This must be done as fast as possible with as few instructions as possible because, as I said, TLB misses happen more often than page faults. This sounds like it would slow down the program again, but it's really a non-issue because strategies were developed to improve performance of software-based management of TLBs. More information on page 204 in the textbook, but basically the fact that the TLB is managed not by hardware but by software is really a non-issue. Either way, if we have a TLB miss, we need to go to the page table that's loaded into memory and perform the indexing operations needed to locate the page being referenced. In short, if what we're looking for was already in the TLB, good, we don't have to access memory. If not, we have to access memory, which is bad. It slows down the program. But if we need to access that page again, we can just put it in the TLB. With software-based TLB management, there are two kinds of misses. The first one is a soft miss. This occurs when the page reference is not in the TLB, but it's in memory. In this case, we simply need to update the TLB. That takes only a few nanoseconds. A hard miss is when the page reference is not in the TLB or in memory, rather it's on the disk. We need to load that missing page from the disk into memory. This takes several milliseconds, which is a million times more time compared to a soft miss. A soft miss requires updates that take on the order of nanoseconds to perform. A hard miss takes updates that are on the order of milliseconds to perform. A millisecond is 1 million nanoseconds, so really it takes a million times longer. These kinds of memory traversals is called a page table walk, by the way. So it's a lot more complicated than just hard versus soft. If a page wasn't found in a process's page table, but it was instead loaded by a different process, then that is a minor page fault. We just simply need to update the page table. A major page fault is when a page needs to be brought in from the disk. Finally, there is a third type of fault. A program may access an invalid address. No changes to the TLB are required. Rather, instead, the OS just flat out kills the process. You may know this as the seg fault, the segmentation fault. Okay, so let's get back to page tables. So larger memory spaces require more pages, and more pages means larger page tables. So how does the system deal with large page tables? Here's one option. We just make the page table have multiple levels. So we page the page table. So this is used for 32-bit addresses. So here we have a 32-bit address that is divided into 3 parts. The first 2 parts are for page tables 1 and 2. The third part is the offset. As I said, we're basically paging the page table. So the top level page table is used to keep track of which second level page tables are or are not loaded into memory. Some of these second level page tables are so important that they must always be loaded into memory. Those that aren't are just swapped in and out of memory as needed. Much like how we can swap in and out pages of a program as needed. So, parts 1 and 2, those are for accessing page tables 1 and 2. When we use PT1 and PT2, we use that information to figure out which second level page table to use. PT1 says, what second order page table are we looking at? And PT2 says, where in the second order page table are we looking at? So it's much like how we use a page number and offset to figure out what page to look at and where in the page are we looking at. PT2 and the offset are used the same way as they would with a single level page table. PT2 says, what page in the second order page table are we looking at? What page are we looking at? The offset says, where in the page are we looking at? So basically we're doing this twice. What page table are we looking at? And where in the page table are we looking at? And then, what page in that page table are we looking at? And where in that page table are we looking at? So there's 2 levels of paging going on. First is to find the page table that we need to look for, and the second one is to find the page in that page table. If we page the page table, we cut down on the amount of memory needed to load the whole page table. Basically, each of these page tables takes up 1024 bytes of memory. Probably more than that, but basically each page table has 1024 entries. And this is for a 4 gigabyte memory space. So we need 1 million entries for every 4096 byte page. Instead of loading everything into a page table that has 1 million entries, we page the page table, so we only load parts of the page table that are 1024 entries each. This reduces space needed to load the page table, so we do need another page table for accessing the parts of the page table that are loaded into memory. The top level page table is used to access the different second order page tables that are loaded into memory. The second order page tables can be swapped. Let's do some math here. We have 32-bit addresses, which means our address space can go up to like 4 billion unique addresses. With 12 bytes for the offset, we have 2 to the 12th power bytes for each page, or 4096 bytes. With 10 bits for PT1 and PT2, we have 1024 page tables, each with 1024 entries of their own. And there's one more page table for referencing one of the 1024 different page tables. 1024 times 1024 times 4096 is about 4 billion. 4 gigabytes of memory. So let's try this out with an address. So first thing we gotta do is we need to convert each hexadecimal digit into their corresponding 4-bit binary number. Then we just gotta divide this into 10, 10, and 12 bits. That is PT1, PT2, and the offset. This simply means page 3 of page table 1, offset 4. Also keep in mind that these values are 0 indexed. Page 3 of page table 1 corresponds to some physical page frame. We then combine that with the offset to get a physical address. So page 3 of page table 1 is going to correspond to some physical page frame. Let's call it frame 67. We combine that with our offset so that we convert page 3 of page table 1, offset 4, into frame 67, offset 4. Technically, we get the page frame number solely from the second level page table. We just needed information from the first level page table to figure out what second level page table to access. So there are 2 arrows going to here when it really should be just 1 arrow. If that page wasn't loaded to memory, the OS, that is a page fault, and the OS will simply load that missing page and update the page table. So this 2-level paging system demonstrated here can work for an arbitrary number of levels. The Intel 32-bit 808386 processor fits the description that we saw here. So it consists of what's called a page directory with entries for 1 page table each. Each page table has its own entries, 1 entry per page. This page directory had 1024 entries. Each page table being referenced has entries for 1024 pages. Each page reference has 4096 addresses, exactly like we saw here. Things get interesting when we get to 64 bits. So initially, the Intel Pentium Pro introduced a 3rd level of paging called the Page Directory Pointer Table. Let's call it the PDPT for short. Each entry was then extended from 32 bits to 64 bits, allowing for memory spaces to exceed 4 gigabytes. Initially, the PDPT only had room for 4 entries. The page table had room for 512 page entries, and each page table had room for 512 page entries. So that's 1 million 4 kilobyte pages, which is still 4 gigabytes of memory. So basically, initially the system was still limited to 4 gigabytes of memory. So when 64-bit support was finally added, not by Intel but by AMD, not only did we see the introduction of a 4th level of paging. This is called page map level 4. We're just gonna call it PML4. But now, finally, every level of page table can now support 512 entries. So now we have 4 levels of page table. So basically, let's do that again. PML4 had 512 entries, 1 for each PDPT. Each PDPT had 512 entries, 1 for each page directory. Each page directory had 512 entries, 1 for each page table. Now we're this is multiple levels of paging. And finally, each page table had 512 entries, 1 for each 4096 byte page. 512 is 2 to the 9th power. 4096 is 2 to the 12th power. So this is 2 to the power of 9 plus 9 plus 9 plus 9 plus 12. Or 2 to the 48th power, which equates to 280 terabytes of addressable memory. It looks like they could have kept going, but they figured that no one was ever going to need that much memory. Famous last words? Bill Gates allegedly said that 640 kilobytes of memory ought to be enough for anybody. This is likely a myth, but this is a myth that still persists to this day, even long after we've exceeded 640K, and still long after we've exceeded 4 gigabytes. Most Windows operating systems these days max out at a few hundred gigabytes of memory to a few terabytes of memory, depending on the version. Unless it's a 32-bit version, and then it's just gonna max out at 4 gigabytes, full stop. If we are going to exceed the 2 to the 48 power limit of memory addresses, it might be a while until we do, if we ever reach that limit at all. Also, final time, Windows 10 support officially ends next year. Windows 11, there is no 32-bit Windows 11. It's all 64-bit. Famous last words? We'll have to see. We'll have to see if there's any one system that might need more than 2 to the 48 memory addresses. Okay, so there is another alternative for page tables for large memory spaces, and that is the inverted page table. It's an alternative to having a paging hierarchy. So instead of one entry per page of virtual address space, there's one entry per page of physical page, one entry per page frame of physical memory. Each entry keeps track of what process and virtual page is using each frame. I'm not gonna get too in depth about it. You can just read about this more on page 208 of the book. But in cases where the address space of programs exceeds the physical memory of a machine, having an inverted page table can save huge amount of space, but it does have its downsides. Virtual to physical translation becomes harder. When a process N references page P, the hardware can no longer find the page frame just using P. It must use N and P together to search each entry in the inverted page table one by one. Again, more details on page 208. So, now we get to the interesting part about our whole discussion on paging, and that is page replacement algorithms. So early on in the slides, we talked about point 1 and point 2. Point 1 was the different ways we can organize the page table. Point 2 is selecting a page frame in which to load a missing page. When a system page faults, the system chooses a page frame to load the missing page. And if there's a page already there, we gotta unload it so we can make room for the new page. So really the question is, how does the system choose a page frame to hold the newly loaded page? Ideally, we would like to choose a page frame whose contents have not been used in a while. Because if we just randomly choose some page frame, then there's a good chance that there is a page in there that we're gonna need again. That means we're gonna have to unload the page only to need to load it again. That is extra overhead of paging out and paging in that we would like to avoid. Additionally, and these are considerations that may be brought up in CSE-4610 that we're just gonna brush off here for now. I'm just gonna give you the Cliff Notes version. Basically, some processes may take, depending on the policies on a computer system, some processes may take page frames from other processes. This sounds unfair, but it is perfectly reasonable for a computer system to allow happen. Basically, some processes may become inactive, so any resources, in this case memory, allocated to that process is just resources that could just be used for other processes. If a process becomes inactive, any resources allocated to it are basically doing nothing. That is grounds for reclaiming resources to give back to other processes. If that process becomes active again, we can just reallocate new resources to it, no problem. Also, some processes are higher priority than others, so they're gonna need more page frames to make sure they have enough memory for the work that they need to do. This is a topic that may be discussed further in CSE-4610, but basically, if a newly made process needs page frames, it may take them from other processes. And to an extent, if an existing process needs more page frames, it may also take them from other processes. Again, this is a topic that may be discussed in CSE 4610, but I'm just giving you the simplified version of what can happen. Anyway, before we continue, as I am recording this, I am teaching both CSE 4600 and 4610, and I'm using two different textbooks for this. Both textbooks contain the same information, but there are parts of what I call the dinosaur book, that's what I'm using for 4610, that I like better than the Carnival book. That's what we're using here. Additionally, the dinosaur book was published when Windows 10 was new. The Carnival book was published when Windows 8 was new. And because Windows 11 is now a thing, they're both outdated. So I think one day I'm going to have to switch over to the 11th edition of the dinosaur book. We'll have to see. My point is, there is an example in the dinosaur book that I think is too good to pass up. So basically, I've adapted that example for use in the Carnival book. So basically, we're gonna need to start with a few rules here. When a process runs, it's going to generate some memory addresses, and we can use that sequence of addresses to create what is called a reference string. Suppose when we trace a process as it executes, it gives us this sequence of memory addresses. And let's just say, for the sake of example, that these are decimal addresses. At 100 bytes per page, we can then reduce those addresses, the sequence of addresses, into what we call a reference string. Consecutive references to the same page are counted as one page reference. Hence why this string is shorter than the original. And we can use this string to compare the performance between different page replacement algorithms. For the sake of time, I think I want to have your final be part of your final, I want it to be you writing a paging simulator. But I'm going to have you do like 1 or 2 page replacement algorithms. So stay tuned and keep watching, because this information will become important for when you do your programming assignment. That is going to be part of your final. To determine the number of page faults for a particular reference string and page replacement algorithm, we need to know the number of page frames available. This assumes that we use something called demand paging. When a process is loaded, none of the pages associated with it are loaded into memory. We only load pages when they're demanded by a process. In the extreme case of one page frame, that means every time you need to access a new page, there's going to be a page fault every time. So we're going to look at 3 page replacement algorithms and see how they perform against one another. We're going to use this reference string here to see how well each algorithm performs against one another. There are more page replacement algorithms than this, but we're just going to start with these 3 for now. Maybe I'll give you the Cliff Notes version of all the others as well. Okay, so the first one is called optimal page replacement, often abbreviated as OPT. This algorithm is so good that we can't implement it in practice because we require future knowledge of how it's going to perform. Alternatively, this algorithm requires information that we cannot determine ahead of time. If we have a sequence of memory addresses, then we can determine which pages they'll be referenced. We have a reference string. We're going to be using that instead. If a page is referenced, it may be referenced later or never again. So, let's step through this reference string 1 page at a time. So, we're going to be assuming demand paging. That means when we begin, none of the pages are loaded into any of our page frames. That means our first 3 page references begin with 1 page fault each, because well, they were never loaded into memory to begin with. When we have a page vault, that means the system must load in that missing page. So for the first 3 memory accesses, we have 3 page vaults. So now we have pages 7, 0, and 1 loaded into memory. When we get to the 4th page in the sequence, we are accessing page 2. When it comes to selecting which page frame in which to load that page, we select the page that won't be used for the longest amount of time. So let's look at this string. So we have page 2, and we want to load it into one of the page frames that has page 7, 0, and 1. So of those pages, I'll tell you right now that the answer is page 7. But why is the answer page 7? Well, so with pages 7, 0, and 1 already loaded, well, we need page 7 again. 1, 2, 3, 4, 5, yes we do. But it won't be used for like 14 more steps. Well, we need page 0 again. Yes! It will be needed right after we need page 2. And will we need page 1 again? Well, yes, because 1, 2, 3, 4... We'll need it 10 steps from now. So, we need page 7, 14 steps from now. We need page 0 right away. And we need page 1, 10 steps from now. So, page 7 is the best candidate to do page replacement. We take out page 7 from memory and put page 2 in its place. When we get to page 5, we perform this algorithm again, but hey look, we already had page 0 loaded into memory, so we don't need to do anything here. Let's get to page 6. So now we are trying to access page 3. We select the page that won't be used for the longest amount of time. Okay, so currently we have pages 2, 0, and 1 loaded into memory. We will need page 0 immediately, so we have to keep that. Page 2 will be used like 3 steps from now, so we gotta keep it. Page 1 won't be used until 8 steps from now, so we unload page 1 from memory, and we put page 3 in its place. When we get to the 7th page, this is actually page. Okay, so when we get to the 7th page, that is page 3, we select the page that won't be used for the longest amount of time, but already contains a page that we already loaded, so we go to page 8. So yeah, there was a typo here. So this was supposed to be page 0 being accessed, but that was already loaded, so we just go to page, so we go to the next page reference, that is page 4. So when we try to load page 4, we'll notice that it's not loaded into memory, so we gotta select the page that won't be used for the longest amount of time. So of those pages, we want to select among page 2, 0, and 3, which of these won't be used for the longest amount of time. Turns out they'll be used immediately after, but of those, page 0 will be accessed the last. That means page 0 is the best candidate, so we unload page 0 from memory, we put page 4 in the place of page 0. When we get to the 11th page reference, we're accessing page 0. We're accessing a page. Okay, so now, it's a little bit confusing, so my apologies. So, at this point, when we get to the 11th page reference, we have pages 2, 4, and 3 loaded into memory. So, pages 2, 4, and 3. Which of those won't be used for the longest amount of time? So, we are here right now, and remember, the pages are 2, 4, and 3. Will we need page 2 again? Yes. Will we need page 4 again? Look ahead in the string. We don't have page 4 anymore. So that means page 4 is the best candidate to do page replacement on. So we need to load page 0 into memory, but we won't need page 4 ever again. So we just unload page 4 and put page 0 in its place, we can continue this process of loading and unloading pages, and at the end, we have 9 page faults. Every time we needed to load a new page into one of those squares, that is 1 page fault. So we have a total of 9 using optimal page replacement on this reference string. As mentioned before, we cannot implement optimal page replacement outside of simulations. Much like shortest job first, we cannot implement optimal page replacement in practice because it requires information that we cannot determine ahead of time. That said, we can use it for simulations and as a means of benchmarking and seeing whether some other page replacement algorithm could be improved. So if we run OPT on a program and it had 9,000 page faults, we can use that as a baseline for improvement. So if one algorithm yielded 9,100 page faults, then it might not be worth our time finding a better algorithm. But if a different algorithm yielded 23,000 page faults, yeah, there's room for improvement there. So the next one is called FIFO page replacement. First in, first out. So basically everything is in a FIFO queue. The first 3 pages referenced begin with a page fault each because none of them were loaded in memory. So the first 3 pages being accessed in the string have 1 page fault each. After that, we have pages 7, 0, and 1 loaded into memory. When we want to access page 2, we unload page 7 and load page 2. So basically, it's first in, first out. It's a line. It's a queue, I should say. We unloaded page 7 because that was the last page to be loaded of the 3 pages that we had. Page 7 is loaded, we load page 2. We look at the next page here, that is page 0. We already have that in memory, so we don't need to do anything here. Page 3 is the next page we're referencing. So we previously had pages 0, 1, and 2. If we want to make room for page 3, we push out page 0 from the end and add page 3 at the front. So there is a push-pop operation going here. We push the next page that we want, and we pop the last page from the end. For the 7th page reference, we're accessing page 0, but we already have that, so we... Okay, so for the 7th page, we are referencing page 0. We pop 1 from the end and push 0 at the beginning. We continue this process of pushing new pages and popping old pages. So at the end, we have 15 page faults. Every time a page was popped to make way for a new page, that is a page fault. So we have 15 page faults. Compared to OPT, this is worse. But as I said, we can't implement OPT in practice. But can we do better? The answer is yes. But before we get to that, FIFO makes for an easy to understand algorithm, but the performance may not be good. It may be the case that when you do FIFO page replacement, you end up popping a page that you're going to be needing again. So you may be replacing the same page often. That reduces performance. Let's look at least recently used page replacement. Okay, so for this one, we have a data structure that operates like a stack. Whenever a page is accessed that is present in this stack, we move it to the top. If a page being referenced isn't in the stack, we remove the page at the bottom of the stack, and then we push the new page to the top. Pages at the top are the most recently used page, and because of the rules here, the least recently used page just moved. They get moved to the bottom. They get moved to the bottom. It turns out for us to implement this algorithm, it isn't cheap because we need to update the stack for every page reference. but there are algorithms out there that approximate this behavior, so we don't have to update it every page reference, but instead we need to update it every, say, 100 page references. There are ways to do that, but I think I'll have to get to that in the next video. Technically, this is not a stack. It is not a stack. It's basically a linked list with special rules for moving pages towards the front. This naturally moves less used pages towards the back. I'm just gonna pretend that it's a stack anyway, with a top and a bottom for ease of understanding. That's also why our little squares are up and down instead of side to side. Okay, once again, when we begin with LRU page replacement, we start off with none of our pages loaded into memory. We load each one by one. So now we have pages 7, 0, and 1 loaded into memory. If we want to load page 2, we pop page 7 and push page 2. If we want to access page 0, hey, we have that in memory. But because of the rules that we have to follow, we move page 2 to the top of the stack. At page 6, we access page 3, so we pop page 1 and push page 3. At page 7, we are accessing page 0 again, we just move that to the top of the stack. At page 8, we access page 4, so we pop page 2 and push page 4. We repeat this process again and again with each time we access a new page. This results in 12 page faults. Not as good as OPT, but better than FIFO. So yeah, those are the performances for 3 different page replacement algorithms. I want it so that for your final, you're gonna actually program 2 of these page replacement algorithms. I wanted it to be your 3rd lab, but I think for the interest of time, I'm just gonna merge your lab with your final. So anyway, there are more algorithms out there that we're not gonna talk about just yet. I think I'll do that in the next video. These are the not recently used algorithm, the second chance algorithm, the clock algorithm, and LRU approximating algorithms that we're gonna talk in section 3 out of 4.7. There are even more things that I would like to talk about in memory, but I think I'm just gonna forgo them in the hopes that your next instructor for 4610 will cover them. Okay. With that, you may notice that your assignments are now being graded a lot later than I want them to be, but they are being graded. So if you have any questions about that, let me know. If there are any discrepancies, let me know. So yeah, with that, I think now is a good time to end this discussion so we can then focus on... Okay, so my plan is sometime next week, you're gonna get your instructions for your final. Because part of those instructions are basically a lab. So yeah, I'm gonna end this discussion here, and next week you might see your final instructions already. And if not week 14, then week 15. Then you would have 2 weeks to finish up your lab. For now, sometime next week you'll get the next video on memory, and it's just gonna be a Cliff Notes version of these other algorithms here. And after that, I wanted to get into how multi-core chips work, but I think I'm just gonna forgo that as well. And instead, I'm just gonna give you a Cliff Notes version of security and protection. Okay? With that, I think we're done for the day, and yeah, we'll meet up in the next video and see where we go from there. Alright, have a good day, and thank you for watching.